The night sky has always carried more than stars. It carries whispers, traces of fire, brief scars upon darkness, flashes too swift to catch with certainty, yet powerful enough to alter the mind. Meteors, the ancient messengers of a cosmos that seldom speaks directly, but instead writes fleeting lines across the ceiling of our world. They arrive as visitors unannounced, silent until air itself becomes their voice. Imagine lying beneath the stillness of a sleeping landscape, trees fixed in silence, the horizon wrapped in shadow, and above an infinity of darkness pierced by the sudden incision of light. For a heartbeat, the sky splits open, a brilliant filament glows and fades, and the night resumes its silence. Yet something has been transferred in that instant, a memory older than Earth, a fragment of a story begun long before the first oceans stirred. For most, meteors are wishes whispered in the dark. But beneath the beauty lies something profound, something unnerving. Each streak is matter untethered from its original home shards of ancient collisions, broken faces of asteroids, dust trails of comets dissolving in sunlight. They are letters written billions of years ago, thrown outward by forces we scarcely understand, traversing the void to finally burn themselves into our atmosphere. Every falling ember is a reminder that our planet is not alone, nor sealed away. Space is not empty, but alive with wandering stones. They fall at all hours, unnoticed except for the rare spectacle when atmosphere transforms them into luminous fire. Some vanish in the upper layers, leaving only vapor trails. Others survive the plunge, reaching the ground as fragments of alien history, older than continents, older than oceans, older than the very crust upon which we sleep. To watch a meteor is to witness the brief union of two realms, the cold, infinite expanse and the fragile envelope of Earth. They arrive not on our schedule but theirs, crossing the boundaries of night with no warning. It is a reminder that our world is porous, that the sky is not a barrier but a gateway where fire becomes the translator of stone. And so, the mystery begins here, in the stillness of night pierced by streaks of light. What are they truly? What do they carry? And why have they haunted our imagination for as long as we have lifted our gaze toward the stars? Long before telescopes sharpened our eyes, long before laboratories could slice dust grains into isotopic fingerprints, there were only the human gaze and the memory of the sky. Meteors arrived then as omens, flashes of divine script that people tried to read as warnings or promises. To witness one was to feel the boundary between heaven and earth thinned to a mere veil. In Mesopotamia, the scribes of Babylon etched careful records of falling stars, associating them with the will of gods and the fates of kings. The sky was their calendar, their courtroom, their map of destiny, and when a fire scratched across its surface, it was interpreted not as stone but as speech. Among the ancient Greeks, philosophers such as Aristotle proposed that meteors were no more than atmospheric exhalations, vapors ignited high in the air. For centuries, this theory held, convincing generations that meteors were phenomena of weather, not visitors from space. And yet, across the continents, indigenous traditions treated meteors with reverence. To some Native American peoples, a falling star was a spirit racing across the sky. In Polynesian navigational lore, meteors marked the pathways of ancestors guiding the living across oceans. In China, court astronomers kept meticulous meteor logs, their careful notations entangling natural events with political outcomes. The first eyes gave them many names: shooting stars, sky arrows, celestial sparks. None of these names carried the suggestion of their true origin, but each reflected an emotional truth, awe mixed with fear. In a world where night was absolute, where fire belonged only to earth, the sudden appearance of light from above was incomprehensible. It is important to remember how radical the true story would one day seem. For millennia, humanity lived under a misapprehension, convinced that these streaks were atmospheric illusions, not messages from beyond Earth. The truth that stone could fall from the sky was dismissed as superstition. Learned men scoffed at peasants who brought forward strange rocks, claiming they had dropped from the heavens. For scientists of the Middle Ages and Renaissance, such claims were madness. After all, how could solid matter exist in the incorruptible heavens? And yet, those first eyes had seen something real. They had given meteors a place in myth, in prophecy, in story. In their fear and their reverence, they were closer to truth than the skeptics who dismissed the very possibility. The mystery of meteors began here, in this tension between the poetic conviction of the ancients and the stubborn refusal of early science. It would take centuries before humanity, armed with new methods and sharper skepticism, would be forced to admit that the stones falling from the sky were not illusions at all. They were emissaries from beyond Earth, and their fall carried a weight of history older than humanity itself. For centuries, the idea that stones could fall from the sky was ridiculed. Learned men scoffed at farmers who swore that a fiery rock had landed in their fields. Professors dismissed villagers who arrived at universities with blackened stones, claiming they had watched them descend from the heavens. The doctrine of the time insisted that the heavens were immutable, incorruptible. Matter, it was said, did not wander the celestial realm. To suggest otherwise was to invite derision. And yet, one by one, the stones continued to fall. The reports accumulated like whispers, each one straining against disbelief. The turning point arrived not in a quiet village, but with a spectacular event that could no longer be ignored. In the year 1492, in the town of Ensisheim in present-day France, a massive meteorite crashed into a wheat field. Weighing over 300 pounds, it could not be explained away as trickery. The people declared it a divine sign. The Holy Roman Emperor Maximilian himself visited the stone, treating it as an omen for his reign. Though interpreted through faith rather than science, this moment marked one of the earliest widely recorded falls in European history. Still, skepticism endured. It was not until the late 18th century that systematic study began to erode doubt. The French naturalist Jean-Baptiste Biot played a decisive role. In 1803, a dramatic fall near the town of L'Aigle in Normandy shattered the old disbelief. Thousands of stones rained down from the sky in broad daylight, witnessed by an entire community. Biot was sent by the French Academy of Sciences to investigate. He mapped the strewn field, interviewed dozens of witnesses, and collected fragments. His report was undeniable. Rocks from the sky were real, and they were extraterrestrial. The announcement shook science. Suddenly, the heavens were not pristine but populated with wandering debris. The Earth was not separate from the cosmos, but immersed in a vast stream of matter. The paradigm shifted overnight, and what had once been superstition became fact. Meteorites, those blackened stones once mocked as curiosities, were revealed as emissaries of worlds beyond our own. The shock was immense. In a single revelation, humanity had to reframe its relationship with the sky. The barrier between Earth and the universe had been broken. The heavens were no longer untouchable. The ground beneath our feet could be struck by matter that had journeyed for billions of years across distances our minds could scarcely imagine. This was the first great rupture in understanding, the moment when stones from the sky ceased to be myth and became a scientific fact. It was a discovery that forced humanity to confront not only its place beneath the stars, but the vulnerability that came with that position. The Earth was not sealed, not safe. It was a target, as it always had been, in a cosmos filled with wandering messengers. Once the stone leaves the emptiness of space and plunges into Earth's embrace, the sky itself becomes a furnace. The boundary is invisible to the eye, yet for a meteoroid, it is a wall of air dense enough to ignite. Speeds range from 11 to 70 kilometers per second, faster than any bullet, faster than any human machine. In an instant, the molecules of nitrogen and oxygen ahead of the intruder are compressed and heated, glowing with the ferocity of plasma. What we see from the ground is not the rock itself burning, but the air screaming around it. The process is ablation. Fragments peel away, vapor trails curl behind, atoms ionize, and the atmosphere becomes luminous. A thin shell of molten material forms, only to be torn off by the hurricane of speed. This is why meteors, though often small as pebbles, flare so brilliantly. The energy is not in their size, but in their velocity, the energy of motion converted into heat and light in a blink. The phenomenon creates more than beauty. Sonic booms follow large fireballs, rolling across landscapes like distant thunder. Infrasound waves too deep for human ears spreads through the atmosphere, detectable by instruments thousands of kilometers away. The sky itself becomes a listening device, carrying the signature of each falling body. At times, the trail persists, twisting in upper winds. A glowing filament lingers, a smoke-like scar that writhes against the stars. These afterimages, called persistent trains, are composed of ionized atoms and dust suspended 80 kilometers above ground. They can shimmer for minutes, shifting shape as if the sky itself remembers the passage of its visitor. This is the laboratory that nature provides. A meteoroid, accelerated for eons by celestial mechanics, subjected in seconds to temperatures hotter than the surface of the Sunday. The atmosphere acts both as shield and storyteller, disintegrating most arrivals while displaying their fiery signatures for all who look up. It is a paradoxical threshold, hostile to stone, generous to sight. For humanity, this spectacle has always been more than physics. To see a line of fire across the heavens is to glimpse the dialogue between void and air. It is the same process that protects us from constant bombardment and yet allows us to read the universe's history, written in light and shock waves. Each streak is the violent unmasking of a wanderer, the brief biography of a stone undone by atmosphere. And still, some survive. For every 1,000 that vanish in fire, a few endure the passage, cooling as they fall, shrinking in speed until they touch the ground. Those survivors, dark, scarred, yet intact, carry within them the secrets of their birthplaces. But before the stone can rest on earth, it must endure this trial of fire, where speed is transfigured into brilliance and silence into thunder. Beyond the spectacle of fire in the sky lies the greater story of where meteoroids come from. Their journey is not random, it is carved by cosmic histories, each fragment born of violence or decay in the wider solar system. To trace a meteor is to follow its ancestry back through collisions, disintegrations, and the quiet work of sunlight over millions of years. Many are children of asteroids. In the main belt between Mars and Jupiter, stone collides with stone, shattered by impacts that have played out since the earliest epochs. Each collision sends fragments adrift, some locked into orbits that will never touch Earth, others nudged by Jupiter's gravity onto chaotic trajectories. The Yarkovsky effect, tiny pushes from the way sunlight warms and re-radiates from a rotating body, slowly steers rubble across space, inching toward resonant pathways that can fling them into the inner system. Out of these processes, new meteoroids are cast, silent voyagers that may one day flare across our skies. Others trace their origins to comets. Unlike the fractured rocks of the belt, comets are icy bodies born from the colder reservoirs of the Kuiper Belt and Oort cloud. As they swing close to the sun, their surfaces boil away, leaving trails of dust and pebble-sized fragments. These streams linger in orbit, forming rivers of debris that Earth annually intersects, giving rise to meteor showers. When we watch the Perseids or Leonids, we are not merely witnessing sparks of rock, we are watching the soft shedding of a comet's body, each meteor a reminder of an ancient icy traveler dissolving into light. There are rarer parents too. Some meteoroids break away from Mars or the Moon, ejected by powerful impacts that blast material beyond their world's gravity. These exiles drift until their paths cross ours, carrying in their mineral veins the signatures of alien surfaces. To hold such a meteorite is to cradle a piece of another world, a fragment of Mars's basaltic plains or the Moon's ancient highlands. Thus, the origins of meteors are multiple but unified in their story. They are fragments of larger bodies, released by collision, erosion, or catastrophe, and set adrift on celestial currents. Every streak of light is not just an object, but a narrative of worlds colliding, of orbits reshaped, of sunlight gently steering rubble through aeons. When a meteor flashes overhead, it is tempting to imagine its journey as sudden, born in the instant of fire, yet its true voyage is unimaginably long. It has drifted for millions, sometimes billions of years, long before humanity raised its eyes to the stars. That grain of dust or fist-sized rock has circled the sun countless times, crossing paths with planets, bent by gravity, altered by radiation, until at last, chance has brought it to Earth. The next time a meteor burns above us, it is worth remembering. It is not simply a fragment falling at random. It is the final act of a cosmic story written far away, a stone exiled from its birthplace, a survivor of collisions, guided by subtle forces, finally consumed in a single blaze. Its light is both an ending and a revelation of the endless dynamics shaping our solar system. The appearance of meteors is not always random. Sometimes they arrive with the precision of clocks, a choreography written in orbits. These are the meteor showers, those predictable nights when the sky seems to weep fire. Their recurrence is not an accident, but the outcome of long trails of cosmic debris released by parent bodies that still wander the solar system. Consider the Perseids. Each August, Earth glides through the dust stream left by Comet Swift-Tuttle, a giant icy traveler with an orbit spanning more than a century. As our planet plunges into its wake, the particles collide with our atmosphere at nearly 60 kilometers per second, igniting the northern summer sky with dozens of streaks each hour. These meteors are fragments of ice and dust freed from the comet during its solar approaches, dispersed along its orbit like breadcrumbs scattered across the night. The Leonids tell a more violent story. Their parent, Comet Tempel-Tuttle, sheds debris that sometimes collects into dense knots. When Earth collides with these clusters, storms occur thousands of meteors per hour, a sky alive with fire. Historic Leonid storms of the 19th century astonished humanity, filling the heavens with what seemed like endless rain of sparks. To watch was to feel the dome of the world collapsing in fire. And yet, it was only Earth passing through a cosmic river of dust, a reminder that our orbit intersects the leftovers of fragile bodies unraveling under solar heat. Not all showers trace to comets. The Geminids, one of the most reliable and brilliant of annual displays, originate from 3,200 Phaethon, a rocky body more asteroid than comet. This challenges the assumption that only icy wanderers produce meteor streams. Phaethon, heated fiercely on its close approaches to the Sun, sheds dust like a crumbling ember, leaving a trail Earth meets each December. The Geminids blaze slower and brighter than most, revealing their stony parentage in the density of their light. Every meteor shower is thus a kind of calendar tied to Earth's steady orbit and the debris rings we intersect. The nights of their appearance are predictable, but their intensity varies, depending on how freshly the parent body has shed its skin of dust. Each shower is a performance of cosmic erosion, a sky lit not by chance, but by recurring passages through trails of ancient decay. For humanity, these showers have become ritual. Festivals and vigils are timed to their return. Photographers climb mountains to capture the radiant arcs. Children are told to make wishes, yet beneath the poetry lies astronomy's quiet calculation. Precise orbits, streams of dust, and the slow unraveling of comets and asteroids over eons. The predictable rhythm of meteor showers tells us something profound. Earth is not solitary in its path. It crosses the tracks of other bodies, sweeping through trails of debris left long before humans existed. Each shower is the intersection of worlds, where the memory of a comet or asteroid dissolves nightly into streaks of flame. In this way, meteor showers are both celebration and elegy, the last light of fragile bodies written upon the vault of the sky. Not every meteor is equal in its brilliance. While most dissolve as faint streaks at the edge of sight, some blaze with such intensity that they turn night briefly into day. These are the fireballs and bolides meteors of exceptional energy, whose brightness rivals the moon and whose descent may be marked by thunderous echoes. Astronomers classify them by magnitude. A fireball is any meteor brighter than the planet Venus, its light piercing through even the city glow. A bolide is more dramatic still, a fireball that explodes mid-air, releasing its energy in a dazzling terminal flash. Their appearance is not just spectacle, but data, a way to measure the scale of the stones that fall toward Earth. The physics is unforgiving. A pebble can create a fleeting spark, but to carve a fireball requires something larger, objects often tens of centimeters to meters across, traveling at cosmic speeds. The kinetic energy they release as they slam into the atmosphere is enormous. The sky becomes a crucible, vaporizing layers of stone in seconds, producing trails so bright they cast shadows on the ground. Patterns emerge in these dramatic events. Some fireballs fragment, scattering multiple glowing shards across the sky, each breaking apart in cascading bursts. Others flare steadily, resisting until a sudden catastrophic disintegration lights the heavens in one final pulse. The details of these behaviors reveal the inner strength or weakness of the meteoroid, whether it was a dense metallic shard, a brittle stony fragment, or a porous clump of cosmic rubble. And the spectacle does not end with light. Many bolides create sound. Seconds after their passage, rolling booms sweep across landscapes, startling those who witnessed the glow. The sound is the atmosphere's memory of the event, a sonic footprint of energy released tens of kilometers above. Sometimes these booms break windows, shake houses, and sow confusion. Other times they arrive only as a low rumble, a reminder that what was seen was not an illusion, but a physical body colliding with our protective sky. The Earth experiences thousands of fireballs each year, though most occur unseen over oceans or remote wilderness. Networks of all-sky cameras and satellites now record them, building a catalogue of their brightness, trajectories, and frequencies. Each data point adds to our understanding of how much material still wanders the solar system, how often Earth intersects it, and what kinds of bodies endure long enough to create such spectacle. For the witness, though, classification is irrelevant. To see a fireball is to feel the nearness of the cosmos, the sense that the heavens are not unreachable but capable of sudden intrusion. It is an encounter with both beauty and fragility, our atmosphere protecting us by sacrificing the stone, our senses gifted with light that originated far beyond our world. Fireballs and bolides remind us that even in their rarity, meteors are not all whispers. Some arrive shouting, tearing through the dark with brilliance that humbles, frightens, and captivates. They are the brightest syllables in the universe's ongoing story. written briefly but indelibly across the skin of the night. The atmosphere is our shield, but it is not invulnerable. When a large meteoroid enters, it does not always surrender quietly in a trail of light. Sometimes, the stone resists until the forces of air and heat tear it apart at low altitude. What follows is an airburst, an explosion that can rival nuclear detonations in energy, unleashed high above the Earth without warning. The most haunting example remains Tunguska 1908. In the remote taiga of Siberia, a silent intruder from space descended and detonated several kilometers above the forest. No crater was left, but the energy released flattened 80 million trees across 2,000 square kilometers. The blast waves circled the globe, recorded by barometers thousands of miles away. Eyewitnesses spoke of a fireball brighter than the sun, a shock wave that threw them from their feet, and nights so luminous that newspapers could be read outdoors in Europe. The culprit was likely a stony meteoroid or fragment of a comet, disintegrating under immense atmospheric pressure. Its size, perhaps 50 to 60 meters across, was modest by cosmic standards, yet its impact on Earth was vast. A century later, Chelyabinsk in 2013 reminded humanity that Tunguska was no anomaly. On a cold February morning, a 20-meter meteoroid struck the atmosphere over southern Russia. It blazed across the sky with the brightness of a second sun, captured on countless dashboard cameras. Moments later, it exploded with the force of hundreds of kilotons of TNT, shattering windows and injuring over 1,000 people. The blast wave rippled through the city, an invisible hammer born of a stone that never touched the ground. These events revealed the double nature of the atmosphere. It is both protector and amplifier. Without it, Earth would be scarred by constant impacts, its surface battered as the moon's. Yet when a large body disintegrates in its grip, the resulting energy release can devastate regions, all without a crater ever forming. The shield becomes a drum, turning celestial intrusions into resonant booms of destructive force. Science has learned much from these airbursts. Instruments from satellites to infrasound arrays have recorded their energy signatures, allowing researchers to estimate their size and composition. The data suggests that objects of Tunguska or Chelyabinsk scale are rare, striking perhaps once every few centuries. Yet they are not impossibilities. They remind us that the Earth lives in a cosmic shooting gallery, and that the sky's protection is never absolute. For those who watched Chelyabinsk blaze across the horizon, there was awe mingled with fear. The sky itself seemed to betray its serenity, suddenly weaponized by a stone that had circled the sun countless times before its final descent. For scientists, these events are sobering case studies. They highlight not only our fragility, but the importance of understanding meteoroids, their origins, and their behavior. An airburst is more than fire in the sky. It is the atmosphere roaring as it tears stone apart. It is the reminder that our shield, though faithful, does not always spare us the consequences of celestial encounters. Sometimes, it turns a silent intruder into a thunderous message. The cosmos is closer and far more powerful than our daily lives allow us to remember. Some meteors survive their fiery descent. Against the odds, fragments endure the furnace of entry and reach the ground intact. These are meteorites, stones that once drifted silently in the dark, now transformed into relics cradled by human hands. They are the most tangible link between Earth and the wider solar system, objects that can be weighed, touched, and studied, each one carrying the scars of its passage through fire. Meteorites are not all the same. Scientists divide them into families, each revealing a different origin story. Iron meteorites are dense, metallic relics, forged in the hearts of ancient planetesimals whose molten cores cooled into crystalline iron-nickel structures. Their interiors gleam with the Widmanstetten pattern, a lattice of metallic bands formed over millions of years, impossible to reproduce on Earth. They are fragments of once molten worlds, shattered in collisions, their cores exposed and scattered across space. Stony meteorites, the most common, are mixtures of silicate minerals. They tell subtler tales of primordial dust clumping together, of heating and alteration within parent bodies. Within their textures lie clues about the earliest days of the solar system, when gas and dust condensed into solid matter. Their surfaces are darkened with fusion crust, a thin skin of glassy rock formed as the outer layers melted during atmospheric entry, proof of their fiery arrival. Then there are stony ions, rare hybrids that blend the two. These are pallasites, with translucent olivine crystals suspended in an iron matrix, gems from the boundary between a parent body's core and mantle. To hold one is to touch the seam between metal and stone, a geological page torn from a long-lost world. Each meteorite is a time capsule. Some preserve minerals unchanged since the dawn of the solar system, older than any rock on Earth. Others carry evidence of water alteration, recording the chemistry of ancient bodies where liquid once flowed. A few even arrive bearing carbon compounds and amino acids, the very molecules tied to the origins of life. Finding them is a treasure hunt. Deserts and Antarctic ice sheets are the best places to search, their barren landscapes offering little camouflage. Hunters scour the plains for blackened stones, distinguishable from earthly rocks by their fusion crust, unusual weight, or metallic flecks. Each recovery extends humanity's collection of cosmic relics, a growing archive of fragments from places we have not yet visited. To cradle a meteorite is to hold a messenger from beyond. It is a reminder that our planet does not stand apart, but is continually touched by the wider universe. These stones are survivors, objects that crossed the sky in fire, endured the atmosphere's violence, and came to rest on soil, ice, or sand. They are the pieces of elsewhere that become part of here, linking Earth to a cosmos still unfolding. Among the most precious gifts of meteorites are the microscopic structures hidden within them: chondrules, calcium, aluminum, rich inclusions, and presolar grains. To the unaided eye, they may look like ordinary rock, dull and unremarkable. But under the microscope, these fragments reveal a record of cosmic processes far older than Earth itself, a library bound in stone. Chondrules are tiny, spherical beads of once molten rock, typically less than a millimeter in diameter. They formed in the solar nebula over 4.5 billion years ago, when dust was briefly flash-heated to extreme temperatures, then rapidly cooled. Each chondrule is a frozen spark from the furnace that birthed the solar system. Their abundance in many meteorites makes them among the most direct witnesses of our earliest cosmic dawn. They tell us that the nebula was not calm, but violent, full of sudden bursts of energy that melted dust into liquid droplets before quenching them into glassy or crystalline forms. Even older are the calcium-aluminum-rich inclusions, or CAIs. These irregular, bright inclusions are the very first solids to have condensed out of the nebula gas. Their isotopic ages pin the beginning of the solar system's timeline. To study a CAI is to stare at the very opening chapter of our planetary story, a piece of matter older than any earthly mineral. Yet hidden deeper still are the presolar grains. These are dust particles that predate the sun itself, forged in the hearts of distant stars, red giants, supernovae, before being carried into the molecular cloud that collapsed into our solar system. Some contain isotopic signatures that cannot be explained by anything within our sun's life cycle. They are whispers from stars long dead, stardust older than our world, traveling for eons before becoming embedded in meteoritic stone. Together, These components transform meteorites into time machines. They encode the chronology of cosmic events, stellar deaths that seeded heavy elements, nebulous storms that melted and reformed dust, and the coalescence of the first planetesimals. They carry within them the memory of astrophysical environments beyond Earth's reach. For scientists, the study of these textures is painstaking. Thin slices are prepared, polished to transparency, and examined with electron microscopes, mass spectrometers, and ion probes. Each analysis yields chemical ratios, isotopic patterns, crystalline alignments. These data points collectively weave a narrative that no human eye could see directly, but which has been written patiently in stone. For the imagination, however, the implications are profound. Every grain that survives to our world has traveled through immense distances and times, bearing in silence the memory of ancient stars and nebular fires. To hold a chondritic meteorite is to cradle not just a rock, but fragments of the cosmos's earliest moments, dust grains that knew the universe before Earth had even formed. What seems a simple stone fallen from the sky is, in truth, a fossil archive of creation. And with each slice, each microscopic survey, humanity comes closer to understanding how matter became planets, and how planets became the stage for life. If meteorites are the archives of cosmic history, then within some lies a subtler, more intimate record, the chemistry of water and carbon. These are the carbonaceous chondrites, dark and fragile stones that hold secrets of life's ingredients and Earth's ancient oceans. Unlike the glittering ions or gem-like pallasites, carbonaceous chondrites appear humble, black, crumbly, easily broken, yet their unassuming appearance conceals remarkable richness. Within their matrix are hydrated minerals, clays, and complex carbon compounds, all formed under conditions far removed from Earth's surface. Their chemistry suggests that, early in the solar system's history, water circulated within their parent bodies, altering the rock and embedding its signature in every grain. These meteorites preserve the fingerprints of that hidden water world. More than minerals, they also carry organic molecules, carbon chains that hint at life's molecular alphabet. Polycyclic aromatic hydrocarbons, amino acids, and sugars have been detected within their structure. They are not life themselves, but scaffolds, molecules capable of forming the foundation of biochemistry. When these stones fell to Earth, they may have delivered not only mass but meaning, helping seed the young planet with the raw ingredients for biology. This possibility reshapes our understanding of life's origins. Perhaps Earth was not entirely self-sufficient in generating the molecules that would eventually form cells. Perhaps rain fell not only from clouds but also from the sky in stone, carrying within it both water and carbon. The oceans we know could, in part, be the legacy of countless meteorites depositing their chemistry across the primordial landscape. The evidence lies in isotopic fingerprints. Hydrogen and oxygen ratios within carbonaceous chondrites sometimes match those of Earth's water, suggesting kinship. This fuels the theory that a portion of our oceans may have come from such bodies, delivered during epochs of heavy bombardment. Each stone, then, was more than debris. It was a courier, contributing to the shaping of a habitable world. For scientists, the study of these meteorites requires care. Their fragile nature makes them vulnerable to contamination. Collected quickly after falls, they are preserved in nitrogen-filled cabinets, shielded from Earth's humidity and microbes. Laboratories become sanctuaries where these fragments are kept as pure as possible, their chemistry guarded against the corruption of time. For humanity, the implication is profound. To gaze upon a carbonaceous chondrite is to see not merely a rock, but a potential ancestor. It suggests that the boundary between geology and biology is not sharp, that life may have been nurtured by cosmic deliveries across billions of years. The black stone, cradled in a scientist's hand, may have carried water molecules that became part of our seas, or carbon compounds that became part of us. Thus, the humble meteorite becomes a vessel of transformation. It connects the silence of interplanetary space with the murmur of tides, the chemistry of dust with the breath of life. And in its darkness lies a reminder. Earth's story has always been entangled with the wider cosmos, written not only in fire and impact, but in water and carbon delivered by stones from the sky. The question of life's beginnings finds one of its most evocative threads in meteorites that arrive carrying the building blocks of biology. Among the most famous of these is the Murchison meteorite, which fell in Australia in 1969. Thousands of fragments were collected, and when scientists examined them, they discovered something extraordinary. Amino acids, the very molecules that stitch proteins together, were embedded within the stone. These amino acids were not earthly contaminants. Their isotopic ratios betrayed an extraterrestrial origin. Within the blackened fragments lay a complex suite of over 70 different amino acids, many unfamiliar to terrestrial biology. They had formed in interstellar clouds or within the watery interiors of ancient asteroids, synthesized in places utterly foreign to our world. The discovery confirmed that space was not barren of chemistry but a vast laboratory, capable of creating the scaffolding of life long before Earth was born. Nor was Murchison alone. Other meteorites have yielded similar finds, sugars like ribose, bases that resemble the nucleotides of DNA and RNA, and even lipid-like molecules that could form primitive membranes. Each compound whispers of possibilities, of prebiotic soups stirred not only on Earth's surface, but also in the void between stars. Laboratory experiments add weight to the story. When scientists simulate interstellar conditions, freezing simple molecules in ice, exposing them to ultraviolet radiation, they find that amino acids and complex organics can indeed arise. The chemistry seen in meteorites may be the natural outcome of cosmic environments, replicated again and again across galaxies. What then does it mean to discover life's raw ingredients within fallen stones? It means that the question of life's uniqueness is unsettled. If the bricks of biology form so readily in space, and if they are delivered across planets by meteorites, then the seeds of life may be scattered widely, waiting only for the right conditions to bloom. The philosophical weight is immense. Meteorites remind us that life's origins may not be an isolated miracle of Earth, but part of a cosmic pattern. The molecules that compose our bodies may once have drifted as dust around another star, condensed into a meteorite's interior, and eventually been flung across space to rain upon a young, restless Earth. For those who study these stones, the work is delicate. Each fragment is a chemical puzzle, its molecules extracted with painstaking precision, analyzed in sterile labs to prevent earthly contamination. Gas chromatography and mass spectrometry unravel their hidden recipes, revealing molecular structures preserved for billions of years. Each result adds another line to the story of how chemistry can lean toward biology without crossing fully into life. And for the dreamer, the implication lingers in the imagination. Meteors as couriers of possibility. They fall through our skies, not merely as streaks of fire, but as reminders that the universe is fertile in chemistry. Each stone is a silent invitation to wonder whether life itself is a universal tendency, seeded across planets by the steady rain of molecular gifts from the stars. Meteorites are more than relics of stone and chemistry. They are also silent recorders of ancient forces, preserving within their structure the traces of magnetism that once coursed through their parent bodies. This remnant, known as paleomagnetism, offers scientists a way to glimpse invisible history's magnetic fields that shaped the earliest worlds and guided the behavior of matter in the young solar system. When molten rock cools, the tiny minerals within it can align with surrounding magnetic fields, locking in a record of their direction and strength. On Earth, this process has allowed geologists to reconstruct the wandering of continents and the reversals of the planet's magnetic field. In meteorites, the same principle applies, but with far greater reach. The fields captured belong not only to our world, but to asteroids, planetesimals, and even the early Sunday. Iron meteorites, once part of molten cores, reveal that their parent bodies generated magnetic dynamos, much like Earth does today. These were miniature worlds with liquid metallic centers, convecting and churning, producing protective magnetic envelopes. The fact that fragments of these dynamos reach us means that even the smallest building blocks of planets experience differentiation and complex internal life before being shattered by collisions. Other meteorites contain magnetized minerals formed on the surfaces of asteroids where water once flowed. Their orientations record local fields, hinting at interactions between solid crusts and the solar system's early magnetic environment. In some, the imprint may even reflect the young sun's ferocious activity, its winds and flares echoing through the nebula, shaping the environment in which planets grew. The tools to extract these whispers are sensitive beyond imagining. Squid magnetometers devices cooled to near absolute zero measure the faintest magnetic signatures still trapped within grains no larger than dust motes. These readings allow scientists to reconstruct magnetic landscapes billions of years old, maps of invisible forces that no eye ever witnessed, but which left indelible marks on matter. What emerges is a picture of a solar system alive with magnetism. Worlds that no longer exist once had active cores. The sun's dynamo blasted out storms that etched themselves into rock. Even as bodies cooled, fragments carried forward the memory of fields long gone. Meteorites thus act as ghost compasses, their mineral needles still pointing to magnets that have since fallen silent. The significance extends beyond geology. Magnetic fields are crucial for habitability, shielding atmospheres from erosion by stellar winds. By proving that small bodies once generated such fields, meteorites suggest that magnetic protection may have been more common than we assume, even among fragile, temporary worlds. Their fragments remind us that magnetism is as fundamental to planetary evolution as gravity or chemistry. To hold a meteorite, then, is not just to grasp ancient matter, it is to cradle a fossil of invisible energy, a silent witness to the unseen fields that shaped the birth of worlds. Its surface may seem inert, but inside it carries the memory of dynamos and storms, frozen forever in stone. Time is written into meteorites with a precision that defies imagination. While myths once described falling stones as messages from gods, science has revealed them to be clocks, fragments, whose isotopes measure the very age of the solar system itself. By examining their radiometric signatures, scientists can date the first dawn of planetary formation, turning meteorites into timekeepers of creation. The process relies on radioactive isotopes, unstable atoms that decay into stable daughters at known rates. Among the most significant is aluminum-2,6, a short-lived isotope that once infused the early solar system. Its decay into magnesium-2,6 provides a chronometer for events in the first few million years after the sun's birth. Within calcium-aluminum-rich inclusions, CAIs, the oldest solids we possess, the ratio of aluminum to magnesium locks in a precise timestamp 4.567 billion years ago. This number, etched into stone, is the birthday of our planetary system. Other isotopes extend the timeline. Uranium decays into lead with half-lives spanning billions of years, allowing absolute dating of meteorites long after short-lived clocks have expired. Samarium to neodymium rubidium to strontium, each pair tells part of the story, confirming that the fragments we hold today have endured since the earliest epochs, surviving cosmic collisions, planetary accretion, and the relentless passage of time. Through these methods, scientists distinguish the relative order of events. Chondrules formed shortly after CAIs, molten droplets cooling within a turbulent nebula. Differentiated meteorites reveal that some parent bodies melted and segregated into cores and mantles within the first few million years, their heat driven by radioactive decay. Others remained cold and primitive, preserving dust grains that predate the sunday. Together, these records map the chronology of creation, from stardust to planets. The precision is staggering. A fragment of Murchison, studied under iron microprobes, yields ages consistent with events billions of years before Earth's crust solidified. Each isotopic analysis narrows the window, aligning across laboratories and methods to confirm that these stones are indeed older than any mountain, older than any ocean, older even than the moon. The philosophical weight is no less immense. When one holds a meteorite, one holds a clock that began ticking before Earth existed. It is a relic not only of matter, but of time itself, a physical measure of a beginning we cannot otherwise witness. In its atoms lies the answer to the oldest human question: when did it all begin? These isotopic clocks do more than date stones. They synchronize the story of the solar system. They allow us to reconstruct the sequence of planet formation, the intervals of heating, the pace of accretion. Meteorites are not random debris but structured records, each bearing a timestamp from a specific page of cosmic history. To gaze at a meteorite through this lens is to see not just rock, but a ticking relic of eternity. Its quiet mass is a calendar that reaches back 4.567 billion years, a testimony that time can be frozen in matter, waiting for minds to learn how to read it. Every meteor tells a story, but some stories are catastrophic, written not in light, but in extinction. Among them, none is more haunting than the tale of Chicxulub, the colossal impact that reshaped life on Earth 66 million years ago. It was a single strike that ended the reign of dinosaurs, silenced ecosystems, and opened the way for mammals to rise. A moment of celestial intrusion that altered the trajectory of evolution itself. The evidence lies buried beneath the Yucatan Peninsula in Mexico, a vast crater, more than 180 kilometers wide, hidden under layers of limestone. Its discovery in the late 20th century confirmed what geology and paleontology had already suspected from subtler signs. A global catastrophe had a single, devastating cause. Around the world, a thin clay layer marks the boundary between the Cretaceous and Paleogene periods. This layer is enriched with iridium, a metal rare on Earth, but abundant in asteroids. Within it are tiny glassy spherules, melted droplets of rock flung into the sky and cooled as they rained back to Earth. There are shocked quartz crystals, their internal structures shattered by pressures greater than any earthly process. Together, these form a signature too clear to ignore, the fingerprint of an impact. The asteroid that struck was immense, perhaps 10 kilometers across, traveling at over 20 kilometers per second. When it collided with Earth, the energy released equaled billions of nuclear bombs. Oceans boiled, forests burned, skies darkened, tsunamis roared outward, and debris launched into the atmosphere spread a shroud that blocked sunlight for months or years. Photosynthesis faltered, ecosystems collapsed, and most species that dominated the land vanished. The Chicxulub impact was not merely a geological event, but a biological revolution. It erased the apex predators of its time, making space for new lineages to thrive. Without it, the age of mammals might never have unfolded, and humanity might not exist. The trajectory of life on Earth was bent sharply by a stone from space. Even in its destruction, Chicxulub carried knowledge. It reminded us that impacts are not rare in the cosmic sense, only rare on human timescales. It showed that Earth's history is punctuated not just by slow change, but by violent intrusions from beyond. The fossil record, with its sudden boundary of loss, stands as proof that celestial stones can dictate the fate of entire worlds. To reflect on Chicxulub is to feel a mixture of awe and unease. The dinosaurs, who reigned for over 150 million years, were undone in a geological instant. The planet endured, life adapted, but the rulers of one age were extinguished by a force they never could have foreseen. The night sky, which had always seemed distant and benign, became in that moment a source of ultimate power. Meteorites, then, are not only timekeepers and carriers of chemistry, they are also reminders of fragility. They remind us that Earth's story is not isolated but woven into the wider tapestry of the solar system, where collisions shape destinies. In the silence of stone lies the echo of a day when the sky fell and changed everything. The Chicxulub impact stands as a warning, but it also prompts a deeper question. How often does the sky strike? Earth is constantly showered with material, from dust grains to house-sized boulders, but the scale of their danger varies dramatically. To understand our risk, scientists measure flux, the rate at which extraterrestrial bodies collide with our world. Each day, the planet is blanketed with an invisible rain of micrometeorites. Thousands of tons of dust drift down annually, unnoticed, filtering into oceans, deserts, and even rooftops. These particles, no larger than grains of sand, pose no threat. Their glow in the sky is gentle, a reminder of Earth's connection to the wider cosmos. Larger meteoroids are rarer, but more dramatic. Objects the size of a grapefruit create fireballs visible to hundreds of kilometers. Meter-sized bodies strike Earth's atmosphere every few weeks, producing sonic booms or scattering fragments across the land. These are not civilization-ending events, but they remind us that our atmosphere is continually tested. The danger sharpens when the scale increases. A 50-meter object, like the one that exploded over Tunguska, could devastate an entire region. Models suggest such events occur every few centuries to millennia. A 100-meter body might erase a city. Kilometers-wide impactors, like the Chicxulub asteroid, strike on timescales of tens of millions of years. Rare, yes, but not impossible. Earth's geological record bears their signatures. Crater counts across the Moon and Mars provide context. Their surfaces, lacking active weather and tectonics, are littered with scars from impacts. By comparing them with Earth, scientists estimate frequencies of large collisions. The Moon shows us what Earth has endured, but also what erosion and plate tectonics have erased from our record. Modern surveys refine these numbers. Telescopes track near-Earth objects, mapping their orbits and calculating probabilities of collision. Statistical models reveal that while civilization-ending impacts are rare, regional-scale airbursts and small strikes are frequent enough to be within human memory. The Chelyabinsk meteor of 2013 was a reminder. Such encounters are not confined to ancient history but belong to the present. For humanity, this knowledge is sobering. The cosmos is not malevolent, yet it is indifferent. Stones wander, orbits shift, and Earth lies in their path often enough that vigilance matters. What protects us is scale. Most intruders are small, consumed in fire before they reach the ground. But the possibility of larger impacts lingers, an unavoidable consequence of living in a dynamic solar system. To measure frequency is to balance fear with perspective. The sky rains constantly, but extinction-level events are rare. Still, the statistics remind us that chance rules over cosmic encounters. On geological timescales, impacts are inevitable. The question is not if another will come, but when and what scale of story it will write upon the surface of our world. Not every cosmic arrival blazes as a fireball or detonates in the atmosphere. Most of what falls is small, almost invisible, tiny specks of interplanetary dust that drift down quietly day after day until the planet is carpeted in their presence. These micrometeorites are the subtle rain of the cosmos, settling on every surface, a constant reminder that space is never far away. Each year, thousands of tons of this fine debris reach Earth. The particles, often no larger than a grain of sand, originate from comets shedding dust and from asteroids colliding in the void. Though their individual arrivals pass unnoticed, together they create a gentle snow of extraterrestrial matter that never ceases. They are the quiet cousins of spectacular meteors, hidden in plain sight. For centuries, such particles were invisible to human understanding, but with careful collection and the rise of modern techniques, their presence became undeniable. Scientists discovered that urban rooftops, far from wilderness, accumulate a surprising amount of micrometeorites. Amid ordinary dust and soot lie tiny metallic spherules and fragile rocky grains, identifiable by their textures and mineral content as visitors from beyond Earth. The same is true in the frozen expanses of Antarctica, where the purity of the ice makes detection easier. There, collectors sift through snow and meltwater, retrieving particles that have rested untouched for millennia. Under microscopes, these grains reveal themselves as jewels of cosmic chemistry. Some are rich in iron and nickel, their surfaces melted smooth by atmospheric entry. Others preserve fragile structures, untouched since they drifted in interplanetary space. Their isotopic ratios carry information about solar activity, the chemistry of their parent bodies, and even the cycles of cosmic dust flowing through the solar system. The scale is immense. Every breath of wind may carry fragments that once orbited the Sunday. The soil beneath our feet hides a steady accumulation of matter not born of Earth. Even the deep sea floor, layered in sediments, contains cosmic dust woven into its strata, silent markers of the planet's exposure to the wider universe. For planetary science, micrometeorites are invaluable. They offer access to material too small to survive as large meteorites, yet rich in diversity. They provide clues to the rate at which comets and asteroids shed debris and how dust streams evolve under solar radiation. They even help trace variations in solar wind over time, as isotopic compositions shift with stellar cycles. But beyond science, they invite reflection. We live surrounded by an invisible rain of the cosmos, breathing and walking through dust older than the continents themselves. It is humbling to realize that every rooftop, every glacier, every desert holds pieces of other worlds, scattered softly like pollen across the planet. To notice them is to feel the universe's nearness. Not all messages from the sky arrive with thunder. Some whisper, arriving as delicate grains that blend into the fabric of our world. They remind us that Earth is never closed, never separate, but always open to the dust of stars. To study meteors is to study transience. A streak of fire lasts seconds, a bolide only moments, and even the brightest trains fade quickly into darkness. Yet science has found ways to capture these fleeting events, weaving a web of instruments across the globe to watch the sky, listen to it, and even feel its vibrations. Humanity has built a sensorium tuned to meteors, allowing us to collect what the eye alone cannot hold. The first line of this network is the all-sky camera. Mounted on rooftops, deserts, and observatory domes, these cameras stare unblinking at the heavens, capturing every flash that crosses their domes of vision. Each night, they accumulate images of fireballs, their trails mapped against the stars, their paths traced across hemispheres. Alone, a single camera provides only a direction. Together, in networks spanning continents, they triangulate, reconstructing the trajectories of stones and calculating their origins in the solar system. Radar adds another layer. When a meteoroid enters the atmosphere, its ionized trail reflects radio waves. Meteor radars detect these reflections, pinpointing speed, altitude, and density. Some systems can record thousands of meteors each night, invisible to the naked eye but clear in the returning echoes. The atmosphere becomes a canvas of signals, where even the smallest grains leave their mark. Sound, too, becomes a tool. Infrasound arrays, designed to monitor nuclear tests, also detect meteor explosions. Low-frequency waves ripple through the air after bolides. Their pressure changes traveling across continents. From these waves, scientists calculate the energy of the blast and the altitude of disintegration. The Chelyabinsk meteor of 2013 was recorded by dozens of stations, its echo circling the globe multiple times. Above Earth, satellites extend our reach. Military and weather satellites have captured fireballs from orbit, their infrared sensors detecting flares invisible from the ground. These records, once classified, now contribute to planetary defense efforts, offering a global perspective of impacts too remote for human witnesses. The integration of these tools forms a net of awareness. Cameras catch the flash, radar traces the path, infrasound measures the explosion, satellites confirm the energy. Together, they transform a fleeting light into a dataset, reconstructing the physics of an event that lasted only seconds. They also allow prediction. By tracing backward, scientists locate the parent body's orbit. By tracing forward, they identify where surviving fragments may have fallen. This network grows ever more intricate. Projects like the Global Fireball Observatory expand across continents, while citizen science initiatives invite amateurs to contribute observations. Smartphones and security cameras, unintended sky watchers, often provide crucial footage of unexpected events. The sky is no longer unobserved, it is watched by a tapestry of human and machine vigilance. For all their sophistication, these tools serve a poetic purpose. They allow us to listen to the fleeting, to give permanence to the ephemeral. A meteor that once vanished into memory now lingers as data, as images, as echoes. Science has learned to hear the stones speak as they fall. And in doing so, humanity has extended its senses into the sky, turning the atmosphere into a vast observatory where every streak, every boom, every whisper of dust becomes part of an ongoing conversation between Earth and the cosmos. Every meteor that lights our sky is not just a falling stone, it is the endpoint of a journey dictated by the invisible mathematics of orbits. To understand why some fragments strike Earth while others wander indefinitely, scientists trace their paths through the solar system, uncovering the forces that sculpt their destinies. At the simplest level, meteoroids follow ellipses around the Sun, like planets do, but their courses are unstable, continually nudged by the gravity of larger worlds. Jupiter, in particular, with its immense mass, acts as a cosmic shepherd. Its resonance's orbital ratios where periods align serve as highways that can fling asteroids inward toward Earth. A fragment drifting quietly for millions of years can, with one gravitational push, find itself on a collision path with our planet. Yet gravity is not the only hand shaping these paths. There is also the Yarkovsky effect, a force so subtle it seems impossible, yet powerful over time. As a small body rotates, it absorbs sunlight and re-emits heat unevenly. This tiny thrust, no stronger than the push of a breath, gradually shifts the orbit, spiraling stones into resonant lanes where gravity takes over. What begins as warmth becomes destiny, steering rubble across millions of kilometers. Collisions between asteroids add chaos to this ballet. Each impact scatters fragments into new orbits, feeding the population of meteoroids that cross Earth's path. Streams from comets follow similar logics, their dust spread along orbits that intersect ours annually, creating predictable showers. All these processes combine into a complex web of motion, an invisible architecture of probability that governs where and when a stone will fall. To track these paths, astronomers use N-body simulations, powerful calculations that consider the gravitational influence of every major body in the solar system. By running these models forward and backward in time, they reconstruct the likely origins of meteorites and predict potential future strikes. Each meteoroid is a wandering equation, its trajectory carved by mathematics as much as by chance. This interplay of forces means that no meteor is an accident. Each fireball we witness is the final step in a long journey shaped by gravity, sunlight, and collisions. The line of fire across the sky may last seconds, but behind it lies a history stretching back millions of years, dictated by resonances and subtle drifts. For the imagination, there is poetry in this. A pebble glowing overhead tonight may have been nudged out of the asteroid belt by Jupiter's pull before the rise of humanity. A grain of dust burning in a meteor shower may have been released by a comet before cities existed. Each trajectory is a reminder that the universe is not static, but in constant motion, where even the smallest bodies are sculpted by forces vast and patient. Thus, meteors are not random visitors. They are participants in the grand mechanics of the solar system, their paths written by orbits, resonances, and the faint but inexorable pressure of light itself. When they strike Earth, they close a long arc of celestial choreography, the last step of a dance begun billions of years ago. Behind the dazzling light of a meteor lies its true character, the material body that carried it across space. Some meteoroids disintegrate high above the ground in a sudden blaze, while others endure the atmosphere's trial and strike Earth intact. The reasons for these different fates lie in their internal architecture, their histories as fragments of larger parent bodies. Asteroids and comets, the parents of meteoroids, are not uniform. Some are monolithic, solid blocks of stone or iron forged in the heat of early planetesimals. Others are rubble piles, loose assemblages of fragments held together only by gravity, products of countless collisions that shattered and reassembled their forms. When a fragment from these diverse bodies enters the atmosphere, its strength or fragility dictates its behavior. Differentiated meteorites, for example, come from parent bodies large enough to melt and separate into core, mantle, and crust. From these worlds, now long destroyed, we inherit iron meteorites from their metallic cores, stony meteorites from their outer shells, and pallasites from the delicate boundary between. These relics show us that planet building was already advanced in the solar system's infancy, and that collisions reduced entire worlds to shards. Other meteorites, the primitive chondrites, are undifferentiated. They never melted, preserving the dust, chondrules, and inclusions that formed directly in the solar nebula. Their parent bodies were small, cold, and fragile, never achieving the heat needed for internal segregation. These bodies, when broken, release meteoroids prone to fragmentation, exploding as airbursts rather than reaching the ground. Thermal metamorphism plays its role as well. Some parent bodies were altered by the decay of radioactive isotopes, heating their interiors and transforming minerals. Others remained unaltered, preserving chemistry unmodified for billions of years. Each stage of this history influences how a meteoroid behaves in its final seconds, whether it shatters at high altitude, survives as a fragment, or crumbles to dust. Even porosity, the empty spaces within, matters deeply. Rubble pile fragments, riddled with voids, tend to break apart easily, dispersing their energy in the atmosphere. denser metallic fragments resist, punching through layers of air to deliver themselves intact to the ground. The variety of meteorite falls reflects this diversity. Some arrive as large iron masses, others as showers of stony fragments scattered across fields and deserts. To study meteorites is to reconstruct their parentage. Scientists examine mineral textures, isotopic ratios, and metallic structures to trace them back to bodies in the asteroid belt or beyond. Each type is a page from a different parent world, destroyed yet preserved in pieces. By analyzing them, we glimpse the diversity of small bodies, how they formed, evolved, and broke apart under the violence of the early solar system. What seems a random stone falling in fire is, in truth, the remnant of a world. It may be a fragment of a shattered protoplanet, the cooled metal of a vanished core, or the untouched dust of a nebula older than Earth. Each meteoroid carries the memory of its parent body, and in its fate, explosion, survival, or disintegration, we read the story of its strength, its fragility, and its long journey to our skies. While many meteor showers follow familiar rhythms tied to icy comets shedding dust with each solar passage, there are exceptions that challenge these simple rules. Among them, the Geminids and the Taurids stand apart, rewriting assumptions about where meteor streams come from and how they evolve. The Geminids blaze across December skies with slow, bright streaks, producing one of the most reliable showers of the year. Yet their parent is not a comet, but 3,200 Phaethon, a body that looks and behaves more like an asteroid. Phaethon follows a highly elliptical orbit, swinging perilously close to the Sun, where its surface heats to extreme temperatures. Unlike comets, it shows little visible activity, no glowing coma or tail. And yet, year after year, Earth crosses a dense stream of dust that unmistakably traces back to Phaethon. The implication is startling. Not only icy comets, but also rocky asteroids can shed enough material to seed a meteor shower. In Phaethon's case, the shedding may be caused by thermal fracturing or dust lofted by solar radiation, turning a seemingly inert rock into a reluctant mimic of comets. The Taurids, meanwhile, are a sprawling and complex system. Their stream is wide, producing not just annual showers, but occasional swarms of large fireballs. The source is likely Comet Encke, itself thought to be a remnant of a much larger progenitor that broke apart thousands of years ago. The torrid stream contains multiple filaments, dense knots of debris scattered across a vast orbital highway. At times, Earth passes through richer parts of this network, sparking an increase in bright fireballs. Some researchers suggest that the Taurids may even hide large, undiscovered bodies, potentially hazardous asteroids traveling with the swarm. These exceptions reveal that meteor showers are not simple, uniform rivers of dust. They are dynamic, evolving structures shaped by the fragmentation of parent bodies, the pull of planetary gravities, and the subtle push of radiation forces. Some streams fade into obscurity, their particles dispersed. Others grow more dangerous, containing fragments large enough to survive as meteorites, or even to cause local devastation should they strike. For astronomers, the Geminids and Taurids serve as reminders to expand definitions. Comets are not the only source of meteor showers. Asteroids too can produce streams, and streams themselves can hide surprises. Not only dust but boulders, not only showers but risks. For those watching from the ground, however, these complexities are invisible. The sky does not reveal the nature of its parent bodies, it only offers streaks of light, falling in graceful arcs. Yet behind each shower lies a hidden story, a history of breakups, fragmentations, and evolving orbits. To witness meteors streaming from Gemini or Taurus is to see the echoes of ancient catastrophes, the remnants of bodies torn apart and scattered along their paths. In these showers that break the rules, the cosmos reminds us that even the most predictable of spectacles is born of chaos. Each falling spark is a fragment of disruption, a reminder that the architecture of the solar system is not fixed but in constant flux, its bodies breaking, shedding, and seeding our skies with fire. The human eye sees a meteor as a streak of white or yellow light, yet hidden within those fleeting flashes is a spectrum, a rainbow of signatures revealing the chemical identity of the stone as it burns. Each meteor is not only a visual spectacle, but also a spectroscopic event, a moment when atoms announce themselves in color before vanishing into ash. When a meteoroid enters the atmosphere, its atoms and the surrounding air are superheated to thousands of degrees. Electrons jump to higher energy states and then fall back, releasing photons at specific wavelengths. To the naked eye, the combined emission appears as a streak of light, but to a spectrograph, the glow unravels into fine lines, each one tied to an element. Sodium flares golden, magnesium shines green, calcium blazes violet, iron leaves a forest of faint bands across the spectrum. These colors are not uniform. A single meteor may shift hue as it fragments, its outer layers burning differently than its core. A sudden burst of sodium produces a yellow flash, followed by the emerald glow of magnesium. The train it leaves may shimmer red as oxygen and nitrogen in the atmosphere recombine. What seems to the casual observer a simple streak of light is in fact a rapid symphony of changing chemistry. Spectroscopy of meteors provides more than beauty, it provides insight. By analyzing the emitted lines, scientists deduce not only composition, but also velocity, altitude, and even the degree of atmospheric interaction. Some meteors reveal high metallic content, suggesting an origin in differentiated bodies. Others show volatile, rich signatures, tracing back to comets. Occasionally, spectra reveal exotic components, traces of rare elements that expand our understanding of solar system diversity. During meteor showers, these spectra become comparative records. Perseid meteors, tied to Comet Swift-Tuttle, often display prominent magnesium and iron features, while Geminids from asteroid Phaethon show distinctive sodium depletion. Each shower carries a spectroscopic fingerprint, linking skyfire to its cosmic parent. Technological advances make these glimpses more precise. High-speed spectrographs attached to all-sky cameras capture emission lines in milliseconds, freezing the moment of chemical revelation. Amateur observers too contribute, attaching diffraction gratings to cameras and building a distributed archive of spectral observations. Each dataset is a small but crucial contribution, turning ephemeral light into lasting evidence. Beyond the science lies a deep, poetic truth. Color is one of the most primal human experiences. To know that the green of a meteor comes from magnesium, the yellow from sodium, the red from atmospheric oxygen, is to merge perception with knowledge. It transforms the night sky into a chemistry lesson, written not on a chalkboard but in the flames of stones older than Earth. In the end, the color of a meteor is both fleeting and eternal. Fleeting because the light fades within seconds. Eternal because its spectrum is a signature, a unique calling card of matter that once circled the sun and now dissolves in Earth's sky. To witness such color is to watch the elements themselves speak in light, before vanishing forever into darkness. The drama of meteors is not confined to Earth. Beyond our skies, other worlds bear witness to the same rain of cosmic debris, but in forms altered by their unique atmospheres or lack thereof. To study meteors on the Moon and Mars is to glimpse how universal this phenomenon is, and how different it appears when the protective veil of Earth's air is stripped away. On the Moon, there is no atmosphere to cushion the fall. Every impactor, no matter how small, strikes the surface at full cosmic velocity. Even a pebble traveling at tens of kilometers per second can gouge a fresh crater in lunar regolith. over billions of years, this relentless bombardment has scarred the Moon into its current state, a pocked and cratered archive of impacts, where Earth's weather, oceans, and tectonics erase traces of meteors. The Moon preserves them all. Each pit, from microscopic divots to the giant basins visible from Earth, is a frozen testimony to collisions stretching back to the solar system's youth. Mars tells a subtler story. With its thin atmosphere just 1% of Earth's pressure, it provides some resistance, but not enough to fully protect its surface. Meteoroids often survive their descent, creating fresh craters that orbiters detect in real time. NASA's Mars Reconnaissance Orbiter, with its powerful high-rise camera, has photographed dozens of such new scars, often surrounded by dark ejecta blankets where the reddish dust has been freshly disturbed. These craters sometimes reveal subsurface ice, hinting at hidden reserves and offering accidental windows into Martian geology. In 2022, NASA's InSight lander recorded something even more dramatic: the seismic signature of meteoroid strikes. For the first time, humanity listened to the rumble of impacts on another world. The lander's seismometer captured vibrations from stones slamming into Mars, and follow-up orbital imagery confirmed the fresh craters. These events connected sound, sight, and surface in a way never before achieved on a foreign planet. Studying meteors beyond Earth serves science in two profound ways. First, it helps us measure impact rates across the solar system, refining our models of how often planets are struck and how hazards evolve. Second, it reveals the roles of atmospheres, how their thickness, chemistry, and density determine whether meteoroids flare into light, break apart in airbursts, or carve directly into the ground. By comparing Earth, Mars, and the Moon, we gain a spectrum of outcomes, from fire in the sky to silent scars. For reflection, there is poetry in knowing that meteors are not uniquely ours. They are a universal language of matter, colliding with worlds. While we gaze at streaks of fire, the Moon quietly accumulates new craters, and Mars echoes with faint seismic whispers. The same stones that awe us at night are shaping landscapes on other worlds, unseen but no less real. To imagine standing on the Martian plains and watching a fireball trace across the thin, pinkish sky, or standing on the Moon and seeing a flash of light as a meteoroid strikes nearby, is to feel the shared vulnerability of planets. Everywhere in the solar system, the story is the same. Stones fall, worlds remember. Though most meteors vanish in fire long before reaching the ground, their remains continue to shape our world in quieter, less visible ways. Tiny particles, vaporized at high altitude, seed the upper atmosphere with dust and smoke that linger for days or weeks. This invisible residue becomes a sculptor of skies, bending light into delicate glows and even altering the chemistry of the air we breathe. When a meteoroid burns, it releases a plume of metal atoms, iron, magnesium, sodium, mixed with the fragments of its vaporized stone. At altitudes above 80 kilometers, these particles coagulate into nanometer-scale dust, known as meteoric smoke. Too small to be seen directly, these grains drift through the mesosphere, serving as nucleation sites where water vapor can condense. From this subtle process arise some of Earth's most ethereal spectacles. Noctilucent clouds are among them. Forming at the edge of space, they shimmer in electric blue and silver, visible only during twilight when the sun lights them from below the horizon. These clouds are seeded, in part, by meteoric dust cosmic grains acting as scaffolds for ice crystals in the extreme cold of the upper atmosphere. Their very existence is a reminder that meteors leave not only fleeting streaks, but long-lasting effects written into the sky itself. Meteoric smoke also contributes to the zodiacal light, a faint, triangular glow visible on dark nights after sunset or before sunrise. This glow, caused by sunlight scattering off interplanetary dust, includes the residue of countless meteors ground into microscopic fragments. It is the softest, most subtle trace of cosmic matter, turning the night sky into a canvas illuminated by dust between worlds. Beyond beauty, these particles affect climate in minute but measurable ways. By altering the chemistry of the mesosphere, they influence ozone balance and radiative transfer. Their role is delicate, not catastrophic, yet it illustrates how the smallest meteoric remains can ripple into atmospheric processes that subtly shape Earth's environment. The study of this dust is challenging. Instruments carried on sounding rockets and satellites collect or detect meteoric smoke, while radars track its influence on atmospheric layers. Even the polar stratosphere shows traces of extraterrestrial metals found in ice cores that trap the fallout of centuries. These investigations remind us that the boundary between Earth and cosmos is porous. The atmosphere is continually infused with dust that began as rock orbiting the Sunday. For reflection, the idea is humbling. Each meteor, though brilliant in its passing, continues its influence invisibly long after its light is gone. The faint shimmer of noctilucent clouds, the pale glow of zodiacal light, the chemistry of air, all carry the fingerprints of matter from beyond Earth. Even the subtlest beauty of the sky is, in part, a gift from meteors. Thus, the falling stone is not only a spectacle of fire, it is also a quiet architect of atmosphere and light, reshaping the upper reaches of our world with every grain that burns. What fades in seconds above our heads lingers in whispers, etched into clouds, glows, and the chemistry of the heavens. The story of meteors is not only one of beauty or curiosity, it is also one of transformation. When large bodies strike Earth, they do more than gouge craters. They ignite forests, stir oceans, loft dust into the stratosphere, and shuffle the delicate balance of climate. In their violence, meteors act as agents of planetary change, forcing life itself to adapt or perish. History offers many such lessons. The Chicxulub impact is the most famous, but smaller events have also altered Earth's biosphere in profound ways. Each time a sizable stone collided with our planet, the atmosphere became a conduit of upheaval. Shock waves flattened landscapes. Fires spread across continents as superheated ejecta rained back down, kindling vegetation. Soot and aerosols veiled the sun, plunging regions into prolonged winters. These processes did not simply scar the surface, they shifted the rhythm of life. When sulfate-rich rocks are struck, vaporized gases rise into the stratosphere, where they form droplets that scatter sunlight. Cooling follows. Conversely, carbon-rich impacts may release greenhouse gases, warming the climate long after the dust has settled. In both directions, meteor strikes have acted as planetary thermostats, abrupt, chaotic, and uncontrollable. The fossil record records these upheavals as punctuation marks. Sudden disappearances of species, bursts of new diversification, strange turnovers in ecosystems all can trace part of their story to celestial intrusions. Evolution has been sculpted not only by slow adaptation but also by moments when the sky itself intervened. In a sense, meteors are editors of life, their punctuation reshaping the narrative of biology. Even smaller events, like Tunguska or Chelyabinsk, hint at this duality. Though they did not rewrite climates, they remind us that impacts are capable of injecting energy into Earth's systems with startling immediacy. Had Tunguska struck a populated city, human history would remember it not as a Siberian curiosity, but as a global tragedy. Modern science explores these dynamics through models and experiments. Computer simulations reveal how ejecta plumes spread, how fires consume landscapes, how oceans absorb and redistribute impact energy. Laboratory shock experiments mimic pressures that form exotic minerals, reproducing the violence of collisions in controlled settings. Each test refines our understanding of how meteors act, not merely as visitors, but as catalysts of transformation. And yet, there is a philosophical thread here too. Impacts are neither good nor evil. They are indifferent, part of the natural order of a solar system in motion. But their indifference does not lessen their significance. Each one is a reminder that Earth's story is not written solely from within. The trajectory of our climate, our landscapes, even our very evolution has been nudged and sometimes jolted by stones that arrived uninvited, bearing the power to reshape the world. When meteors fall, they may carry amino acids, or water, or nothing but silence. But when the large ones strike, they carry change itself. They are viruses of transformation, infecting Earth with sudden shifts that ripple across epochs. Life, in response, adapts. And humanity, aware of this pattern, lives in the knowledge that one day another such stone may once again edit the script of our world. If history shows us that impacts can reshape climates and life, then the natural question follows: how do we prepare for the next one? In the modern era, meteors are no longer only omens to be feared or curiosities to be studied, they are also challenges to be anticipated. The science of planetary defense has emerged as humanity's attempt to turn awareness into protection, to foresee the next stone before it strikes. Surveys form the foundation of this effort. Across mountain deserts and volcanic plateaus, wide-field telescopes sweep the night for faint moving points of light. Projects like the Pan-STARRS survey in Hawaii, Catalina Sky Survey in Arizona, and the forthcoming Vera-C Rubin Observatory in Chile map thousands of asteroids, plotting their orbits with exquisite precision. Each detection is a new piece of the cosmic puzzle, a calculation of whether and when it might cross Earth's path. Space-based observatories complement them. NASA's NEOWISE mission, for example, scans the sky in infrared, detecting dark, carbon-rich asteroids invisible to optical telescopes. Planned missions like NEO-SURVEYOR will extend this vigilance, turning space itself into a sentry that can spot potential hazards long before they approach. Once discovered, objects are classified and monitored. Scientists calculate probability ellipses, forecasting where an asteroid might be decades from now. Most threats vanish under repeated observation as orbits refine into safety. But a few remain stubborn, their futures uncertain, lingering as reminders of potential danger. The question then becomes, what can we do if one is truly inbound? Here, imagination meets engineering. Concepts range from the kinetic impactor striking an asteroid with a high-speed spacecraft to nudge its orbit to gravity tractors, spacecraft hovering nearby for years, tugging gently with gravitational pull. Even solar sails and focused beams have been proposed, subtle methods of altering a stone's path long before it arrives. In 2022, the DART mission transformed speculation into reality. NASA deliberately crashed a spacecraft into the asteroid Dimorphos, altering its orbital period around its parent Didymos. The test proved that humanity could, with enough time, change the trajectory of a celestial body. It was not destruction, but deflection, a push sufficient to demonstrate that the principle works. Yet even with vigilance, uncertainty persists. The population of small to medium objects, tens to hundreds of meters wide, remains incompletely catalogued. These are large enough to devastate a region yet too faint to be easily tracked. They are the Chelyabinsk's and Tunguska's of tomorrow, reminders that while global killers are rare, regional threats remain present. Thus, planetary defense becomes a balance between humility and ambition. We cannot stop the cosmos from sending stones our way, but we can strive to detect, measure, and, if necessary, alter their course. In doing so, humanity steps into a new role, not only a witness to meteors, but an active participant in the choreography of celestial mechanics. It is a remarkable thought. For billions of years, Earth endured impacts without defense, its surface scarred by unrelenting rain. Now, for the first time, a species has gained the awareness and tools to intervene, to anticipate, to perhaps spare the world from another catastrophic strike. The sky remains unpredictable, but no longer completely beyond our grasp. Even with telescopes sweeping the heavens and spacecraft testing deflection, the truth remains: certainty is elusive. Predicting impacts is not a matter of absolute yes or no, but of probabilities, shifting numbers refined with each new observation. To live under a sky filled with wandering stones is to live with statistics, and science has learned to translate those uncertainties into tools for planetary defense. When a new near-Earth object is discovered, astronomers plot its orbit using limited data. Early trajectories are wide corridors of possibility, uncertainty ellipses stretching across millions of kilometers. With more observations, these corridors narrow. Sometimes the risk evaporates entirely, the orbit resolving into harmlessness. Other times, a small but persistent probability lingers a fraction of a percent, a chance that decades from now, Earth and asteroid might meet. To manage this, scientists use impact scales. The Torino scale communicates risk to the public, ranking potential events from 0, no hazard, to 10, certain global catastrophe. Most discoveries rest at 0, their risks erased with further study. Occasionally, a 1 or 2 appears normal levels of near-Earth encounters worth continued monitoring. Higher numbers are vanishingly rare but not impossible, and their appearance triggers global attention. Behind these scales lies mathematics. Bayesian models weigh uncertainties, updating probabilities with each new data point. Monte Carlo simulations explore millions of possible futures, calculating the odds of collision from slightly varied initial conditions. The process is not unlike weather forecasting. A cone of possibilities narrows with time, revealing eventual certainty. But unlike storms, asteroids move with the patience of celestial mechanics. We may have years, decades, even centuries of notice. Still, the statistics can be sobering. Models suggest that Chelyabinsk-scale impacts occur once every few decades. Tunguska-level events strike perhaps once in 1,000 years. Larger, civilization-threatening impacts are spaced by tens of millions of years. The numbers remind us that while the greatest dangers are rare, smaller but still destructive strikes belong squarely within human timeframes. These assessments feed into drills and preparations. Space agencies and governments conduct tabletop exercises, simulating discovery of an inbound asteroid. They rehearse communication strategies, deflection options, and disaster responses. The point is not to stoke fear, but to prepare to translate abstract probabilities into protocols. For the ordinary person, such numbers may seem remote, detached from daily life, yet there is comfort in the fact that probabilities are being calculated at all. The sky is no longer an unknowable source of fate. With each survey, each statistical refinement, humanity gains a clearer map of the hazards above. The cosmos remains unpredictable, but not opaque. Philosophically, this reliance on probabilities is fitting. Meteors have always embodied chance, an unexpected flash, a sudden fall, a random strike. Science does not erase their unpredictability, but frames it, quantifying uncertainty into scales we can understand. To live with meteors is to live with risk, but risk measured, studied, and perhaps for the first time, manageable. Thus, the statistics become more than numbers. They are a lens through which we see our place in the cosmos. Fragile, exposed, yet not helpless. The sky may always hold uncertainty, but now we meet that uncertainty with knowledge, with preparation, and with a steady gaze upward. Among the fragments that fall from space, some carry messages older than Earth itself. These are the presolar grains, microscopic crystals embedded within meteorites, formed not in our solar system but in the dying embers of distant stars. To hold such a meteorite is to touch matter that predates the sun, matter that traveled across the galaxy before becoming part of our world. Presolar grains are rare but unmistakable. When meteorites are dissolved in acid to isolate their most resilient components, tiny grains remain: silicon carbide, graphite, diamond, and oxides. Their isotopic fingerprints defy the uniform ratios of solar system matter. They contain excesses or deficits of elements that can only be explained by nuclear reactions in stars long vanished. Some record the slow fusion within red giants. Others bear the explosive mark of supernovae, where heavy elements were forged in a single violent instant. Each grain is a message from a star's life cycle. In silicon carbide crystals, scientists detect signatures of S-process nucleosynthesis, the slow capture of neutrons within aging stars. In nanodiamonds, isotopes reveal the chaos of stellar explosions. These grains are cosmic refugees, blown into interstellar space by stellar winds or shock waves, drifting for millions of years until they join the cloud that collapsed to form our Sunday. The survival of these grains within meteorites is astonishing. They endured the turbulence of the solar nebula, avoided melting within parent bodies, and persisted through billions of years in space. Their presence tells us that not all was erased during the fiery birth of planets. Within the most primitive meteorites, untouched by heat or differentiation, these stellar relics remain intact fossils of stars encased in stone. For science, presolar grains open a new dimension. They allow laboratory analysis of processes that occurred light years away, long before Earth existed. In mass spectrometers, their isotopes become evidence of stellar interiors, data more direct than telescopic observation. They turn meteorites into archives not only of our solar system's formation, but of galactic history. For reflection, the significance is profound. We often say that humans are made of star stuff, that the atoms in our bodies were forged in ancient stars. Presolar grains make this metaphor tangible. They are literal fragments of those stars, carried across interstellar distances, arriving in our hands as glittering specks preserved in stone. To study them is to trace ancestry beyond planets, beyond the sun, into the heart of stellar furnaces where the universe manufactured the elements of life. Each meteorite that contains presolar grains is more than a relic of the solar system. It is a letter from before the solar system, written in isotopes, carried across time, and delivered by the fall of stone. In their silence lies a reminder that meteors are not merely visitors from space, but couriers from deep time, bearing evidence of stars that lived and died long before our world began. As the evidence accumulates from amino acids in carbonaceous chondrites to presolar grains older than the sun, to the scars of ancient impacts, it invites speculation about what meteors mean for the broader story of life and existence. They are more than wandering stones. They may be instruments of selection, couriers of chemistry, even editors of planetary fate. Consider their role as couriers. Over billions of years, Earth has been bombarded with meteorites rich in carbon, water, and organics. These deliveries may have jump-started prebiotic chemistry, seeding the planet with ingredients for life. If this process occurred here, it could happen elsewhere. Countless worlds might be showered with similar gifts, each meteor carrying a molecular toolkit capable of nudging barren surfaces toward biology. In this sense, meteors are emissaries of possibility, scattering the seeds of chemistry across the galaxy. They may also act as selection pressures. Impacts periodically reset ecosystems, clearing dominant species and allowing others to rise. The Chicxulub event, catastrophic for dinosaurs, was opportunity for mammals. Smaller impacts too may have shifted evolutionary pathways, forcing adaptations to new climates or environments born of sudden change. In this sense, meteors are editors harsh, impartial, but creative, revising life's script in punctuation marks of stone and fire. Some scientists extend the speculation further. If meteorites can deliver amino acids, could they also carry dormant life itself, microbes encased in protective stone? The hypothesis of panspermia suggests this possibility, that life might spread between worlds via meteorites blasted from planetary surfaces. Though unproven, the idea lingers, supported by the resilience of certain microbes that can survive radiation and vacuum. Each meteorite becomes, in theory, not just a rock but a vessel, carrying biological cargo between planets and perhaps between star systems. Even if life does not hitch rides across the void, the philosophy remains. Meteors remind us that boundaries are illusions. Earth is not a sealed sphere, isolated from space. It is part of a system of constant exchange, receiving material from beyond while scattering fragments of itself outward. In every meteor fall is proof that the universe is interconnected, its parts mingling in endless cycles of impact and dispersal. To speculate about meteors is to speculate about ourselves. Perhaps without them, life would never have begun here, or would have evolved along different paths. Perhaps every living thing carries, at the deepest chemical level, a legacy of stones that fell long before the first cell divided. Perhaps meteors are not accidents, but integral parts of the universe's way of ensuring diversity, resilience, and continuity. Such reflections blur the line between science and philosophy, but that is fitting. Meteors are both material and metaphor. They are solid objects carrying isotopes and minerals, but they are also symbols of chance, of fate, of connection. To look at them is to feel the immensity of time and the intimacy of matter, the sense that every spark in the sky is both a reminder of danger and a whisper of creation. In the end, what meteors suggest is not only scientific truth but cosmic meaning, that the universe writes its story not only in stars and galaxies, but also in stones that fall silently, carrying with them the power to transform worlds. And so the narrative returns to where it began, the night sky, silent and infinite, pierced by the briefest strokes of fire. Meteors have carried us from superstition to science, from omens of fear to archives of creation. They are timekeepers and couriers, destroyers and nurturers, fragments of distant worlds and whispers from ancient stars. To follow their story is to follow the story of Earth itself, for our planet has always been shaped by what falls upon it. As we lie beneath the sky, each streak becomes more than spectacle. It is the visible reminder that the universe is not distant but near, that the void between stars is not empty but alive with travelers. Dust settles upon rooftops, iron cores rest in museum halls, amino acids arrive within fragile stones, and sometimes the heavens roar with explosions that bend history. Meteors embody all of it: beauty, terror, and the quiet persistence of cosmic exchange. In their light, we glimpse the paradox of existence. They are destructive, yet they deliver the ingredients of life. They are fleeting, yet they preserve ages older than Earth. They are indifferent, yet they alter the course of evolution and culture alike. They are reminders that our world is fragile, but also reminders that it is deeply connected to the wider universe. As the fire fades and darkness returns, reflection lingers. Perhaps meteors are not accidents, but the way the cosmos reminds us of our origins, our vulnerability, and our place in a vast ongoing story. They are archives, falling from the sky, each one a page torn from a distant epoch, dissolving into brilliance before vanishing into silence. And now, as sleep draws near, let the mind rest in that silence. Imagine the soft rain of dust settling invisibly across the world, a ceaseless lullaby of matter, older than oceans, older than mountains, older than time as we measure it. Imagine the rare thunder of stone, distant yet inevitable, echoing through the ages, and imagine the universe, infinite and patient, sending its messages night after night until the last ember fades. Here, under a sky both fragile and eternal, one may close their eyes knowing that meteors will continue to fall, quiet witnesses, fiery storytellers, and cosmic companions. The earth turns, the stars wheel overhead, and the stones descend, keeping their vigil. Sleep then, under the falling archive of the universe. Let the memory of light guide you into rest. For tomorrow, and all tomorrows, the meteors will still be their reminders that we are not alone, that we are part of something vast, ancient, and endlessly mysterious. Now, let the pacing soften. The story slows, like twilight settling across a quiet landscape. The violent images of fire and thunder dissolve, leaving only a gentle awareness of continuity. Meteors, once fierce, are remembered here as delicate threads, weaving together earth and sky in a tapestry of calm. Breathe with the thought that every night, without interruption, grains of cosmic dust drift down. They arrive unseen, floating through the air, joining rivers, soils, oceans. Their descent is silent, patient, tender, an endless snowfall of stardust. It has always been so, long before we walked beneath the sky, and it will remain so long after. This is not a storm but a rhythm, one the Earth has known for billions of years. Picture the faintest glow of noctilucent clouds, shimmering silver blue at the edge of vision. Picture the soft veil of zodiacal light, rising like a ghostly pyramid from the horizon. These are the quiet signatures of meteors' presence, the subtle beauty they leave behind once their fire has passed. And then, imagine yourself resting beneath that sky. No threat, no urgency, only the comfort of continuity. Meteors fall, as they always have, yet here in the stillness they are lullabies, each streak a reminder of connection, each grain of dust a reassurance of constancy. Sleep comes easily under such a sky. The universe does not rush, and neither must you. The stones will continue their journeys, the stars will continue their cycles, and the earth will continue to turn. You are part of this turning, part of this rhythm, embraced by the same silence that holds the meteors in their long descent. Rest, then, in the calm of that knowledge. The sky is vast, but it is also gentle. The fire has passed, the dust remains, the night is yours. Sweet dreams.